All right, so we've covered a lot so far. We're wrapping up the chapter. It's the longest chapter in the textbook, and we're talking about compressible flow and jet engines, but especially compressible flow out of the back of nozzles. You can have a compressible flow out of the back of jet engines as well, where the compressible effects have to be accounted for. What's this a picture of? It's a picture of a shuttle with the boosters, the main engines, and you could see that the exhaust from these engines right here, they're saying, with this nozzle, is coming out at Mach 10. And there are some shocks that are visible, little diamond shocks right in this vicinity. Okay. So what is the basics of a rocket nozzle? So here, different than a jet engine where you ingest a lot of mass, a lot of air. Here, the fuel is on board, so it's not ingesting anything. It has the oxidizer and the fuel on board. Okay, so they go into a combustion chamber where the velocity is relatively low. But in the combustion, it's spanking hot, high temperature, high pressure. And then it's looking to exhaust. So you have a converging section of a nozzle, the throat of the nozzle, and a diverging section of the nozzle. You understand converging, the area is getting smaller in the direction of flow, and then diverging, the area is getting larger in the direction of flow. So what happens here is you want the flow to come out close to the ambient pressure, a lot lower pressure than in the combustion chamber. And you want it to come out very, very high velocity. True or false? High velocity good for thrust? True? All right, let me ask the clicker question. So the clicker question is, what is the thrust generated by a rocket engine which has an exhaust speed of 500 meters per second and a mass flow rate of 20 kilograms per second? Everybody in? Let's wrap it up so we can move on. And we'll show the results. And the results show that a lot of people believe it's 10 kilonewtons. Now, why is, right away, thrust, the units on thrust are newtons or units of force. So a watt is no good, and a kilowatt's no good, and a kilojoule. So you only had two to pick from, really based on the unit consideration. And then you take a look and you recall 500 times 20. Can you do that in your head? Is that right? But then you had the units of kilogram per second times meter per second. Kilogram meter per second squared is a 1 newton. So 10,000 newtons, 10 kilonewtons. Congratulations to the 89% who did that correctly. Very good. So there's a derivation of equation. We want to consider one-dimensional flow where you're changing the area for the flow. And the fluid behaves as an ideal gas. So it could change density. True? So this equation right here we're going to derive. Now, the derivation's all on this page. It's all mathematics. But let's take a look at the equation. Do we understand things that are in the equation? What is big M? Mach number. Mach number, true? If it's less, well, I wrote MA, but I think this book uses M without an A. I think a lot of books use MA. I've used MA. And now, what is V? Velocity, speed. What is A? Cross-sectional area. So you're changing the area in which this one-dimensional flow occurs. All right, so what is a dV? It's how the velocity changes, a small change in velocity. What is dA? Change in area. So the area could go down. That would be converging. Or the area could go up. The area would be diverging, right? We're thinking about nozzles and flow through nozzles. Okay, So this equation really tells us how, if I change the area, how the velocity is going to change. And it's a very interesting equation because the Mach number twists things around. We'll explain the equation in a minute, but let's just derive the equation. What do you think m dot equal to a constant is? It's some sort of balance statement. What's it saying? It's a mass balance. M dot in equal to m dot out equal to constant, and then you have a little differential, okay? So in the change, so if you have a small differential now, we take a derivative. This is calculus, because the m dot's a function of small changes in area, small changes in speed, small changes in density. And so we're ready to use this equation. Then we go and get an energy balance or momentum, energy or momentum. But here the textbook uses energy. And we find that dH is related to VdP, not VdP, VdV. And then what do? We have it's like go to an entropy balance or go to a property relationship where there's entropy and say, hey, we have isentropic flow. Even though the area is changing, it's going to be frictionless, it's going to be reversible, it's going to be isentropic. Hence we get this relationship. It all looks very mathematical, but don't forget, mass, energy, entropy. All right. Then we have to put them together. It's slick algebra, putting them together. Little calculus, too, because it's all done on a differential form, right? So we get eliminating dH, you get a relationship. This is probably a little throw off to the side. It's basically a statement of the state principle. What's the state principle? Two independent intensive properties fix the state, hence I can get other properties. So let's say that in principle, density and entropy are independent. They fix the state. If needed, I could get pressure. That's really what this is saying right here. So you could do the same type of chain rule calculus to take the derivative of the pressure. Recall that we are dealing with isentropic flow. We want to restrict ourselves to isentropic flow through that nozzle. Recall the definition of C. I forgot. What is the name of C? Speed of sound, the sonic speed. Okay? And manipulate. See how I'm bringing this down, bring this over, I know it's a little tricky, but it's all in the book too. But there is the relationship. So it's a combination. Isentropic flow, ideal gas, and you've conserved mass and energy, and it's, I already said isentropic, didn't I? And you've used the state principle. So there's the equation. I've just brought it over, just shown it to you again, okay? So we're going to be thinking about maybe flow in what we call a nozzle. Here's a nozzle. How does the area change? How does the area change in the direction of flow? It gets smaller. It's negative. Isn't it negative? It gets smaller. Okay. So we're restricted to constant entropy process. True? Okay. How does the velocity change?
Faster.
It gets faster. It gets faster. True? Does this equation agree with that? Does this equation show that? Sure, let's do it this way. Take this equation and rewrite it like this. Did I do the algebra correctly by rewriting it? Thumbs up if you agree. Good. So now let's do this. I said let's only talk about subsonic flow. If I only talk about subsonic flow, what is m, the Mach number? Less than 1. So what is... This is the numerator, this is the denominator of that quotient or ratio. So what is the denominator? If it's m squared minus 1, and m is always less than 1 for subsonic flow, what is m squared minus 1? Is it going to be a negative? Does everybody agree? Then you have, how does the area change? The change in area over area. That's a negative. Okay, so if I have a negative over a negative, positive, the velocity is going to increase in the direction of flow. That's how you use this equation. Do you like that game? Were you ready to play another game? How about, what do you think's under this box? The diffuser. All right? It's still subsonic. So if it's still subsonic, take a look at this ratio right here. Isn't that still negative? But what about the dA over A? It's now positive. Okay, positive over negative? Negative. So what does dV do? It slows down. It decreases. That's right. It decreases. You're good. Guess what's under the next box? We've already changed the magnitude of how the area changes. We said, oh, let it go down. Let the area go up. Now you're going to change Mach number. If I said it was supersonic, what does that mean about the Mach number? Greater to 1. Go back to this. What does it say about the denominator right here? If its Mach number is greater than 1. Positive, 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 positive. All right, let's go back to something that's shaped like this. The area is converging. The area is getting smaller in the direction of flow, is it not? So what is the dA? Getting smaller over area, which is always positive. Isn't this negative? All right, so if I have negative over positive, is it negative or positive? It's negative. So dV over V is negative. How can that be? It's slowing down or speeding up as I go. You're slowing down. You're slowing down. Okay, look at the area. This was going this way, and it's slowing down. We would call that a diffuser. But doesn't it look like a nozzle? Do you see the two geometric similarities? But the flow is just the opposite because it's supersonic. The Mach number is over 1. First time you see that, you say, something unbelievable is happening. I'm going to be able to regurgitate this for the test, Professor, but you will never make me believe this. True? Isn't this crazy? This is absolutely crazy. All right, so then you go underneath this box, and we do the other shape. What's the area doing here? Increasing. It's an increasing area. It's diverging. Increasing area, diverging section. This was a converging. Let me write it down. This is a diverging section. If it's supersonic, the Mach number is greater than 1, what happens to the flow in a diverging section? Does it speed up or slow down? Looks like it has a lot more room, doesn't it? It looks like it should slow down, but it's supersonic. This is going to speed up. We would call that a nozzle because the flow is speeding up as it goes through it. It looks like a subsonic diffuser, but it's a supersonic nozzle. All of it from this equation. Wow, that equation looks like we have some errors in it. No, it's been vetted. A number of people have checked it out. It works. It's in the textbook too. Go and look at the derivation of it. I know I blew through that derivation quickly, but that's an important equation, isn't it? Here's off a NASA website. What are they doing? Oh, they're talking about nozzle design. And they say a CD nozzle. Oh, everything's abbreviated. A converging, diverging nozzle. So here I have a combustion chamber. Then I have a converging section. Then I have the throat, which is the smallest area where it's changing from converging at the throat. It changes to diverging. Diverging section, what happens to the cross-sectional area for the flow? Gets bigger, larger, right? That's what we're talking about. Converging, throat, diverging, converging, diverging nozzle. Look at this equation, m dot equal to a constant. We just did it. Yeah, the textbook does it. What is this? Calculus. What is this? Well, they did it with the momentum perspective, but we're hot after all the energy. But if you did this in a fluids class, go open up your fluids textbook, go back and look at the compressible flow section. They're probably going to take a momentum, not an energy approach. but it's the same result. You have isentropic flow, and you combine them, and there's our big equation. They made it red. Here is a great little description. They say for subsonic flow, what's that? Mach number less than 1. Increasing area, so dA is greater than 0. It's increasing area in the direction of flow. Causes the flow velocity to decrease. dV is less than 0. Likewise, I've been saying the same thing in words. For supersonic flow, increase in the area causes the flow to speed up, to increase. You all good?
Last call. Anyone have one?
Also, I think I showed this last time, a De Laval nozzle. I don't have a picture of the man. I should get a picture and tell you what years he lived and where he was from and all that. But you can find that out on the internet. But this is a converging, diverging nozzle, and it really kicks out the gases at the exit if you have a high enough pressure in the combustion chamber of that nozzle. So the velocity will get to be, well, actually at the throat you get Mach 1. The velocity is the speed of sound at that temperature, whatever the temperature is in the throat. And then if it's in a supersonic region, the diverging section, the velocity continues to go up. The velocity continues to go up as it's going down that nozzle. So let's go through, back up a little bit and just walk through a classic discussion of the effects of back pressure on a converging nozzle. I'm going to do just a converging, then we'll do converging, diverging. So what we have is we have a chamber that's able to supply a constant pressure. We'll call it P naught, not the back pressure, but a stagnation pressure. And T naught, gas, ideal gas like air, supplied to a nozzle. Here's the nozzle right there, okay? And then we stop the exit of the nozzle. It goes into a large chamber which you can control the pressure on using a valve. So we control the back pressure in the chamber or near the exit of the nozzle. So we're going to talk about the pressure at the exit of the nozzle. We'll talk about the back pressure and the stagnation pressure, supply pressure, P naught. Is that too unclear, P naught? And what we do is we put a plot. I'm going to put a plot like this. This is distance going from the beginning to the end of our converging nozzle. And we're going to plot pressure. Pressure. Now, conceptually, put a large P naught on there. Not so unreasonable, but let's say 10 atmospheres. Okay? That's reasonable, but it's high enough. A nice good 10 atmospheres, right? And if you open this valve outside, guess what the air pressure is outside? 1 atm, 1 atmosphere, okay? So you can make this go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 atmospheres. And let's put P naught equal to 10 atmospheres to begin with, okay? I keep the valve closed. What's the pressure halfway down the nozzle if the valve is closed? It's a really easy answer. It's P naught. How about at the exit? The pressure is P naught. How about way over here? Back pressure. P naught. It's just all the same pressure. I kept the valve closed. So I can plot that as my beginning case. There's the pressure at every point through the nozzle. And out here is the back pressure. True? I open the valve a little bit. Is it going to fall all the way to 1 atmosphere? No. It's going to go to 9 atmospheres, right? So let's say now the back pressure is 9 atmosphere. Okay? So what do you think the exit pressure is right there? 9 atmospheres. The flow is going to be coming out straight like this. The pressure across those streamlines as it exits into this larger back pressure chamber is the same as the back pressure. Okay? So what about the pressure over here? I said the pressure over here is always going to be P naught, 10 atmospheres. Does the pressure go down? Is there a little flow like that? Does that what the pressure does when I open the valve a little bit? Makes sense? Sure. How about if I go to 8? I go to 8 or 7. Sure. It's going to come here. It'll be 8 or 7, go back up here, and it's always steady P naught. I have something to be able to maintain P naught there, the supply. Keep going, keep going. What do you think the velocity is at the exit, the speed at the exit in the first case? 0. What do you think the velocity is at the exit for the second case? A little faster. How about the next case when I drop it to 7? Do you think there's more flow going to be coming out if I drop it to 7 on the back pressure? Yes, that's right. It'll be more. But guess what happens? You can make this drop so much, and if you drop it to around 5 atmospheres, you're going to get something special. Oh, I can open up the valve some more and drop that back pressure to 4 atmospheres. And I can open it up some more and drop it to 3 atmospheres. But guess what happens roughly around 5 atmospheres? The speed comes out at the end of that nozzle at the speed of sound at the end of the nozzle. It comes out at Mach 1. All right. Let's say then I drop the pressure to lower. Do you think that the pressure is going to continue to drop and I'll get even faster flow out the end of that nozzle? No, you won't. What will happen, very interesting, is you'll get a shock wave. You'll get a shock wave, and the flow will maintain its same profile that you had before, and you'll get a shock wave at the exit. And it'll drop that pressure to the back pressure. And so across that shock wave, it is not isentropic. It's highly irreversible. The flow through the nozzle remained isentropic through the whole discussion, but then, boom, it hits, and now we have a shock wave. What about these shock waves, Professor? Well, read the textbook, get another textbook, go online, look up normal shocks, oblique shocks, etc. Well, what is a shock? A shock wave is treated as a discontinuity where the entropy increases over a nearly infinitesimal region. It's just a thin region where the gases have abrupt change, like a line. There's really a no fluid discontinuity, but you put a little control volume around where the shock wave occurs. You look at both sides coming in, pre-shock side, the post-shock side, the going out, and it's a very small depth or thickness to it, and you have conservation of momentum, mass, energy, but you have highly irreversible, and so you have a lot of entropy production. And because of that, well, it's something that's much more difficult to analyze, and I don't. I just say, hey, there are shock waves in the world. This is what they look like, very thin regions, and this is what happens across them. You can have a normal shock, meaning the flow is going this way, and the shock is this way. Guess what's perpendicular? The shock is perpendicular to the flow. You can have an oblique shock, okay? The flow is this way, and the shock is this way. And so the flow isn't perpendicular to the shock. Yes, sir?
So is that why they have CD nozzles, to get rid of the shock waves and keep increasing velocity?
Yes, that's exactly it. Yep. So let me take a look at this. So this is an illustration of my high pressure reservoir which maintains P naught. This is a quick illustration of my converging section. This is a throat, etc. I haven't gotten to the diverging section, so I'll come back to it. But sometimes you can get shocks coming off, oblique shocks coming off of those things. Okay? I don't know how much it's converging or diverging on this aircraft, but you see this little pattern right here? Diamond shocks, shock diamonds in the jet engine exhaust. Okay? So that's what they say is visible. These oblique shocks, they make diamonds crossing over. All right, there's your whole introduction to shocks. Don't ask me more. It's just don't have time, and there's a whole class that I pitched the class before to you. Compressible flow. Somebody in this class took it when they should have taken Thermo 2 first. Who was it? Who was it?
Travis, he's not here.
He's not here. Okay, nobody else took it? How many is interested in it? They can take it next semester, so whenever it's offered next, right? So very much engineering. So what happens is you get a shock, an oblique shock, at the exit. Okay, it'll come like this, something like that, where then there's highly irreversible, but the pressure's got to drop back down to whatever the back pressure is. And it's irreversible, but you're not going to get any more flow. Here's another plot of interest. It's a little hard to understand when you first look at it. On the x-axis, they plot the back pressure divided by that stagnation pressure, the supply pressure. Okay. If it's 1, that's great. If you drop the pressure a little bit on the back pressure and drop the back pressure more and drop the back pressure more, what's going to happen to the mass flow rate that goes through the nozzle? Well, it starts with no mass flow, and it's rapidly going to go up as you drop that back pressure. But then it gets to choked flow. And when it's choked, the flow, regardless of the back pressures here or here or here, it doesn't change the pressure going through the converging nozzle. The converging nozzle always stays subsonic. It always is choked, or Mach 1 at the exit, and the mass flow rate's maximized. So it tapers off when you get to about a half. Yeah, and it'll be one of our equations, which I'm not going to jump to right now, but yes, it's explained in some of the equations as well as a table of the textbook. Makes sense? Same with the velocity. What does the velocity do? It goes and tapers off till it's the sonic speed in the throat. You can't go faster. It doesn't go faster. Well, let's now talk about a converging-diverging nozzle. So now what you do is you have a section that has the converging section, the throat, the diverging section. All right? And what we'll do is we'll do a supply P naught here with T naught. And out here we'll put a control system with a valve. And we'll talk about the back pressure. And we'll also talk about the pressure at the exit of the nozzle. And we can also talk about the throat pressure in the throat. Okay? But let me just leave that off for right now. Okay, so let's go ahead and make a plot as a function of distance, x, where this is the exit, kind of lining up there. This is the throat, line it up there. This is the entrance region, right in there. And so let's say it's a 1 ATM, 2 ATM, 3, 4, 5, 6, 7, 8, 9, 10 ATM. There's pressure going up. And here's P naught at 10 ATM. Great high pressure. It could be 20. That's okay. Let it be 20. Okay. All right. Now, we start with the valve closed. What's the pressure look like everywhere? It's all 10 ATM. We open the valve a little bit. We open it to 9. The back pressure is now 9. What do you think is the exit pressure? 9. Okay, this pressure way over here is still 10. Something happens in between. Does it just go like this? No. Because this whole section looks like a converging followed by a diverging area. Okay, let me ask this. Do you think it jumps all right away to supersonic flow? Could it stay everywhere subsonic? I mean, just say 10, there's no flow, drop it a little bit. You think it's going to stay subsonic? Yeah, it's going to stay subsonic. 10 to 9 isn't enough to make it go supersonic, okay? So it's subsonic. So where's the minimum pressure? At the exit? Well, no. Think about this. All right. How about what happens here? What's happening to the pressure as I move from this in this converging section? Down, down. What happens to the pressure as I go in the diverging section? It's going back up. It goes down, 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 hits a spot, goes up, 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 until it hits the exit. So guess what? That's what the pressure profile looks like, true? Where's the minimum? In the throat. In the throat. Okay? Where we're changing from converging to diverging. Let's say we drop it some more, and maybe the pressure of the throat's even lower. Right? Let's drop it some more, and then we hit some spot. Uh-oh, this pressure gets down to about half of the P naught. It's now Mach 1 right at the throat. But before we get to Mach 1, put in your mind 0.999 Mach, just a little below. If it's just a little below, it hits the throat, then it starts increasing area. What's it going to do? It's just going to stay subsonic, and it's going to recover. Pressure is going to go back up. Now in your mind, you go a little above. You put the pressure, the back pressure, a little bit below, and now the pressure in the throat is sufficient to really bring it all the way to Mach 1, and it really wants to be supersonic, and so it starts to be supersonic as it starts to go into the diverging section. So it'll stay like this. It won't increase above Mach 1. The pressure will stay at that throat pressure, but it'll get even lower pressure further into the diverging section of the nozzle. The flow is now going a little bit above Mach 1. But guess what? You didn't lower the back pressure low enough. Boop. What do you mean boop? What's that? Boop. You're going to hit a shock. You're going to hit a normal shock, which is highly irreversible. There's going to be a pressure bump across it, and then after it, on one side it was supersonic, slightly supersonic. On the other side it's going to be subsonic, and it's going to behave like it is rest of the way subsonic. But you see that the exit pressure and the back pressure are, low. It's lower than before. Guess what happens if I lower the back pressure some more? Going to go further down, hit the shock, and go that way, right? So I made the nozzle a little too long. Sorry about that. Let me change the shape a little bit. But what happens if I walked it out, and right here, it's just right before it would normally hit a shock, come up, pop, and there's the exit pressure, right? Then I lower it a little bit more. Yeah, bring it shock right to the edge. And then I lower it just a little bit more. I can't have a normal shock within the diverging nozzle anymore. Something happens where I get an oblique shock that jumps it up. Let's say I lower the pressure more. I have a shock, but it's going to be nice actually right in there. Let's say I lower the pressure even more. I then get a shock where there's a pressure drop across it. Okay? Soft introduction to something that may take a lot of time to really explain to you in a whole class in propulsion and compressible flow.
I mean, once we decrease it, as long as we decrease the pressure, the flow velocity will increase.
No, at this point right here, your mass flow rate's maxed out. Now you're just having shocks to adjust to the back pressure. Right. Also, the mass flow rate right here, in all of these purple cases where you do have supersonic flow, what's happening is you're not getting more mass flow rate anymore. Your mass flow rate's maxed out. But what happens to the exit speed? It's higher and higher and higher and higher. So your thrust goes higher, 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 not because of increased mass flow rate, but because of increased exit speed, supersonic. well, subsonic. It was supersonic in some of them, but here it's exiting subsonic. But here it would be coming out really fast. And you would get those diamond shocks afterwards. Remember let's go back and look. Do I have it here or here? Right here. That can exit very fast. Oh, back here. Well, what do they say about the exit of those engines right here? Mach 10. Okay. But you get the evidence of some shocks, oblique shocks afterwards. All right, so here is a discussion at the nozzle of a converging, diverging section, and you get these shocks and you get the triangles and expansion. And here's a beautiful, more clear picture of some shocks afterwards. They're more prevalent at the ground level. All right, here's a picture off at a NASA site how the back pressure, ambient pressure, affects the nozzle flow. I don't want to say it's trivial. I don't want to go into all of it, but this is what it shows where they expand out some, is if the ambient pressure is less than the nozzle exit pressure, and then this is a good match, exactly the same, then you have the straight flow. When the ambient pressure is a bit more than the nozzle exit pressure, so then you get some shocks and start to get this formation. And then you can even move those shocks back inside the nozzle if it's much more than the nozzle exit flow pressure. Okay? All right. Well, here's some more equations that we need to be familiar with. This first equation we've already derived and we're familiar with it. True? What does it tell us? It tells us how does the speed change as the area changes for both subsonic and supersonic flow, right? But let's take a look at this equation right here. Well, T naught, isn't that some of that stationary pressure, stationary temperature? That was our subscript naught. They call it the stagnation temperature, T naught. The stagnation pressure, P naught. Usually the introductory, just think of it as what's supplying the nozzle. It's stationary, it's low velocity, and it feeds it. Well, you can also think about the stagnation enthalpy, which is the sum of the current enthalpy at that location plus its kinetic energy. Well, here's an equation showing you what the temperature is doing. Remember we did that last time. What happens to the temperature as you go down the nozzle? It doesn't necessarily stay the same. It typically goes down. Why does it go down? Because the kinetic energy is going up. And H is a function of T. And so if K, kinetic energy, goes up, that part of the total energy, the enthalpy part, goes down, temperature goes down, right? So you can see it in this equation. This equation works for subsonic as well as supersonic flow. So this is saying the physical temperature related to the stagnation temperature is 1 plus K minus 1 over 2 times the Mach number squared. What is K? K, I forgot the name of K. Ratio of specific heats. Okay. How about this one, this equation? This is how the pressure changes compared to the stagnation pressure, and it's a function of the Mach number, how fast it's going. Make sense?
So if that equals 2, Mach number equals 1, roughly?
Yeah, put in a Mach number, or K of, let's say, 1.4. You could put a Mach number of 2 in there, and then you can get that ratio.
We're speaking specifically of ideal gas.
Ideal gases. This is restricted to ideal gases. Otherwise, it becomes, get a computer code. Make sure it's big. So these are our equations, here, here, and here. I have a question for you, a clicker question. So we'll turn it on and see the question. For isentropic flow of an ideal gas in a supersonic converging diverging nozzle, the temperature T is always less than the stagnation temperature T naught. True or false? Are we all in? All right, let's go ahead and shut it down and pull people. And let's see. Well, it's split, isn't it? Well, it's isentropic flow. Can I include any discussion of a shock? Nope. So there's no discussion of shock because it's isentropic, right? And so does this equation apply only when it's subsonic, only when it's supersonic, at all times? When does this equation apply? At all times, right? And so is the Mach number ever negative? Well, even if it is negative, it's squared, but it's never negative. It's 0 up, right? 0 to 1, then it's above 1, right? So look at this equation. How about K? I mean, it's 1.4. It's greater than 1, so this is positive, positive. This is all positive. And so it's going to be greater than 1. Maybe like T naught over T would be like 1.2. Make sense? 1.05. So what about the temperature? T is always less than the stagnation temperature. True. You ready for the next question? Why not? For isentropic flow in a supersonic converging diverging nozzle, P, the pressure, is always less than P naught. True or false? I think everybody's in. We're all in, so let's go ahead and shut it down and see where we're at. Well, we have 81% correct, which is better. There's another, okay, so look at this equation here. You see the Mach numbers, this all positive, positive. It's all going to be greater than 1. Remember also I was plotting, where was that plot? Back here, here, here. What are we plotting? Another way to plot this is if I put it on a scale where it was 1 down to 0, and I could plot P pressure divided by P naught. The ratio the pressure always is dropping below P naught. You see that? It's always dropping below. Where is the pressure the lowest in when the flow is completely subsonic? The pressure is lowest at the well, no, it's at the throat, right when it's subsonic. Yeah, at the throat. So, okay, there's a couple derivations. They're in the textbook. You can see them where you say, what is enthalpy? This is a conservation of energy statement. Apply constant specific heats. There's your T naught. Come over here. What's this? Mach number defined as speed of sound in ideal gas, constant specific heats. Combine them, manipulate, and there you go. Okay? So please take a look at those derivations in the textbook, and we'll continue the discussion Monday.